Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. In this video, I will explain on our last subtopic, which is Hessian function. Hessian function is used to determine the properties of stationary points of a function. Okay, let's say if we have a function, okay, n number of function with n variables, means from x1 x2 until xn, or it can be other notation for variables, for example x, y, z, and so on. Okay, so you can define your variable to be any letter. Okay, so Hessian can be defined as a determinant of second order function. Okay, second order partial derivative of the functions that we have. Okay, so in general, we can say Hessian is a determinant for our n number of functions of variable x1 until xn. So in order to determine the Hessian or determinant, okay, of a function, we need to find the second order of partial derivative of all functions that we have. Alright, so it will be treated like this. Alright, so for the row, this is for variables. Okay, and you will treat your column exclusively for your function. So this is your f1, f2, f3, fn. Okay, so for the first column, you will perform second order partial derivative for function 1 with respect to x1, x2 until xn. Okay, so it will be mixed. Okay, alright. For the second column, it will be exclusively only for the second function. You will differentiate this. You will find the partial derivative of the second function. Okay, the mixed derivative. Okay, for x1, x2, x2 squared until your xn. Okay, and this will continue until your last function. Okay, so if you deal with 2 by 2 matrix, okay, determinant, it will be as usual. You need to perform cross product minus with the cross product of the others. Okay, if you have 3 by 3, then you need to use the other methods that we learn in chapter matrices. Okay, right, so for Hessian, it's not like a Jacobian. Okay, it is fixed where the column would be for your function first, function second until your end function. Okay, and then the row will be for your variables. Alright, while for Jacobian, you can swap row and column to be any of your function, or it can be your variable. It doesn't matter. But for Hessian, it is fixed. So you follow this. Alright. So good news is in this course you will be tested only with one function that have two variables. Okay, so you'll be dealing with a function of two independent variable x and y. So in other words, you'll be dealing with a 2 by 2 matrix. Okay, so for 2 by 2 matrix, to find the determinant for 2 by 2 matrix is easy. You just cross product this minus with cross product of that. So you will get this formula, okay, to find your Hessian, your determinant. Okay, so it will be the second order partial derivative of your variables. Okay, and this is your mixed second order partial derivative. Okay, so it will be square lah, because you get that, because this one cross this one, you will get this. Okay, del f del square f del x square, which is this, and then multiplied with del squared f del y squared, so you get that one. Okay, minus with the product of this, because these two are equal, del squared f del x del y and del squared f del y del x. Okay, they are equal. Remember the property of mixed partial? Okay, it doesn't matter which one you perform first, whether you do first for your y and then followed by x, and then you do the second order partial derivative, but you perform for x first and then followed by y, they will be equal. Okay, this is mixed partial. This is called mixed partial. So the property said they are equal. Thus, this is equal to that, or if you multiply these two, okay, that will be equal to that, or you can also say that. Okay, so in this case we just define it as del x del y squared. All right, thus you'll be using this to find the Hessian. Alright, now let's us go to the next slide, where I will introduce you to the property of a stationary point, where we use Hessian to determine the types of stationary points. Okay, so before we determine types of a stationary point, of course, we need to find the stationary point first. Okay, for a function, there will be a point or points, okay, for that function. Okay, so that we call stationary point. Okay, we call it stationary point. To find the stationary point, we need to set the first order derivative, a partial derivative of the function with respect to the first variable and the second variable to be equal to 0. And once we set the del f del x equal to 0 and del f del y equal to 0, we will get a point or points where that is the location of stationary point. Okay, so it's easy. In order to find stationary point, first you set the partial derivative of your function with respect to your first variable, your x is equal to 0, and then followed by the second condition, which is your partial derivative of your function with respect to the second variable, which is y, also equal to 0. Okay, so by setting these two equal to 0, you will get two simultaneous equations where when you solve them, they will give you points or a point or points that we call stationary point. Okay, and then once we determine what is the location, where is the location of the stationary point or our stationary point, alright, we need to determine types of stationary point, okay, by testing or by looking at the value of our Hessian. So our Hessian will determine types of stationary point. Okay, so there are three types of stationary point. The first one is called saddle point. Okay, the second one, it is either minimum point or maximum point. Okay, and the third one is none of these two. So we say it is no conclusion can be made whenever your Hessian is satisfied certain condition. Alright, so we will look at this condition for the Hessian where to determine the which one of these types of stationary point. Okay, so it is very simple. You test your Hessian, okay, you calculate your Hessian based on the formula that we learned in the previous slide, and then you just substitute whatever value for the second order of partial derivative, then you calculate the determinant, okay, which is your Hessian, and look at the value of the Hessian. If the Hessian is less than 0, okay, so your stationary points, okay, that you got from setting del f del x equal to 0 and del f del y equal to 0, okay, is called saddle point. Okay, so once again, you calculate your Hessian, okay, where the formula is del f del x squared times del squared f del y squared minus with del squared f del x del y squared. Okay, so you substitute the second order partial derivative as in this formula, okay, then you will get the value of Hessian. Look at the value here. If it is greater less than 0, you can conclude that the stationary point that you got from this setting, okay, is saddle point or points. Okay, if your Hessian here is greater than 0, okay, if Hessian is greater than 0, your stationary point has two conclusions. So it is either minimum or maximum. So to determine whether it is minimum or maximum, it cannot be both, okay? It either be minimum like this or it should be maximum, okay? Minimum or maximum for a function, okay? Because you have one function, a function, so your function either be my function or set function. So if it's my function, the possibility is your stationary point will be minimum. And if it is a set function like this, quadratic function to be in a quadratic function to be in this shape, so possibly your stationary point from this setting, okay, this setting is maximum. So from Hessian, we just, if it is greater than 0, okay, there are two possibility there, minimum or maximum, but the result must be only one. So in this case, to determine whether it is minimum or maximum, you need to test for this condition. Okay, you need to test this condition. Alright, so look at your second order partial derivative with respect to your x squared. If it is less than 0, okay, or your second derivative partial derivative with respect to your y is also less than 0, then it is maximum. If otherwise, then it be minimum. Okay, understand? Right? So it is special case for Hessian greater than 0, because the possibility is whether it is maximum or minimum. So it will be just one, maximum or minimum. Okay, so by looking at Hessian greater than 0, you must have the idea that your stationary point would be either minimum or maximum. Which of these you need to test for this? Okay, look at your second order partial derivative with respect to your x and with respect to your y. If it is less than 0, then you conclude it is maximum. Your stationary point is maximum. If your second order partial derivative with respect to your first variable and second variable is greater than 0, then you conclude that your stationary point is a minimum. Okay, and if you find out that your Hessian is equal to 0, you can conclude that there is no conclusion. So test is failed. Okay, your test is failed. You have no conclusion whenever your Hessian is equal to 0. Okay. Okay, let us look at the example to find and to classify the stationary point. Okay, so now you have a function here where this function is depending on two independent variables x and y. Okay, so remember, first step, find stationary point or points. Okay, so it depends on your function. Okay, so in order to find the stationary point, you need to do two things. First, you need to find your del f del x equal to 0, set your del f del x equal to 0, and then set your del f del y also equal to 0. So you will have two equations here. Okay, so let us do that first. Right, so del f del x is, okay, so this is partial, so remember, just concentrate on the variables that you are interested to derive, okay, to differentiate. So it is x, so then just concentrate on x and treat your y as a constant. So that will give you 3x squared minus 6x plus 2y, and this will be 0 because this is a constant. Alright, so this is equal to 0. So you got one equation here. Then set your del f del y also equal to 0. So this will be 0. The second term will be 0. The third term will be 2x. And the fourth term will be minus 2y. Okay, and this is equal to 0. So you have two equations here. You need to solve this equation simultaneously to get the point. Okay, so here from 2, okay, to be easy, let us solve for x here. Okay, so you have x equal to y. Okay, so it is from 2 we get x equal to y, because from here 2x equal to 2y, thus x equal y. Okay, so from 2 you got this. This would be your third equation. Okay, so you sub third equation into 1. Okay, so you will get 3y squared minus 6y plus 2y equal to 0. Okay, and this 3y squared minus 4y equal to 0. Factorize y, you will get y minus, 3y, okay, minus 4 equal to 0. Thus y is equal to 0, or 3y minus 4 equal to 0. That will give y equal to 4 over 3. Okay, so now we have points where when our y equal to 0, our x also equal to 0. So we have point 0, 0. This is our first point. And the second point, when y is equal to 4 over 3, we also have x equal to 4 over 3. So we have second point here, which is 4 over 3, 4 over 3. So this is our second point. So here we have two stationary points. Okay, two stationary points. The first one is 0, 0. The second one is 4 over 3, 4 over 3. So these are 2 points that we need to classify whether they are saddle, maximum, or minimum, or no conclusion. Okay, so these two fall in which category, which type? Okay, so we need to test this. So we need to proceed to number 2, steps 2, which is finding or calculate Hessian. Okay. Okay, so in this slide, this is roughly equal to what I did in the previous slide. Okay, so you will have to simplification like this. And then finally, when you substitute everything, you will get this. Okay, so you have two stationary points here, right? Okay, now we are going to proceed to the second step, which is finding the Hessian in order to determine the class or the type of stationary point that we found in the first or in the previous slide for this particular function. Alright, so just now we have a function which is equal to x cubed minus 3x squared plus 2xy minus y squared. Okay, and we have found that del f del x is equal to 3x squared minus 6x plus 2y, and del f del y is equal to 2x minus 2y, right? Okay, now in order to apply for Hessian, to find for Hessian, we need del squared f del x squared, and then multiply with del f, the square f, del y squared. Okay, minus with the mixed partial. Okay, so after finding the first derivative, okay, we can proceed from here to find the second order derivative. So from here, we perform one more time with respect to the same variable. Okay, from here, start from here. So it will be 6x, okay, minus with 6, because this is a constant. Alright, so we got this. right? And then we will differentiate this partially with respect to the same variable. Okay, you will get del x squared f del y squared. Okay, from here. So this will be constant. This will be minus 2. Okay, so minus 2. Right? So for mixed function, okay, you can either choose to start from with here or with here. It doesn't matter. Okay, it doesn't matter, because if you choose to start from here, you will also get del f del x, sorry, square del x. Okay, so the first will be the del x, and then you will do second time by y. So this will be constant, constant. So differentiate this, you get 2. Or if you choose to use this, okay, you will get the similar answer as well, because del f square del y, okay, del y is this 2x minus 2y. When you do for x, okay, so you will forget about this because this will be constant, so you concentrate on this, differentiate 2x, so we get 2, so they are equal. Okay, so just choose one, that will give you similar answers. So 2. Okay, so after you got all these value, substitute into the Hessian formula. Okay, so 6x minus 6 with and then the multiply with the second one here, which is minus 2, minus with the mix, which is 2. Okay, so where do you get 4 here? Something wrong here. This should be 2, right? This should be 2. Yeah, it is 4, correct, because this is square, I forgot. Okay, square. So this is square. So that's why you got 4 there. Let's delete this back. Alright, so this is your Hessian. Okay, and then you need to substitute the 2 stationary points that you got from the first from the previous slide just now by setting your first derivative with respect to your x and y equal to 0. You got 2 points, right, which is 0, 0, and the second point is 4 over 3, 4 over 3, right? You need to substitute all these points, okay, one by one, each of the points into Hessian. Okay, so substitute what is x is. You don't need y here because you have no y in the Hessian here, so that will give you the value of the Hessian. Okay, same goes to second point. Okay, so let's go to the next slide. Okay, so it is easy for us to perform a table like this so that it is easy for us to see what happened. Okay, and it's easy for us to check later. Okay, rather than we just write it randomly on our paper. Okay, right. So you have first point here and second point in this row. Okay, this is for Hessian. To find for Hessian, x is 0, y is also equal to 0. Since we have no y in here, so we just need information, x information here. When we replace a 0 here, so this will vanish. What we get is Hessian equal to 8. Okay, so h equal to 8. 8, does it greater than 0 or less than 0? It is greater than 0. So the condition said if your Hessian is greater than 0, there are two possibilities, okay, whether the point 0, 0 here is minimum or maximum. So which one of these? To conclude, we need to test for the del squared del f del x squared and del squared f del y squared. If they are greater than 0, then it is minimum. If they are less than 0, then you can conclude that it is maximum. So let us check. Just now we got del squared f del x squared is equal to 6x minus 6, and we already got for del y squared which is equal to minus 2. Okay, so it's fine. So this one you don't need to do any substitution, because it is already a constant which is negative 2, and negative 2 is less than 0, isn't it? Okay, once satisfied for maximum, and check for the x. If you replace 0 here, what will you get? You get minus 6. So minus 6 is also less than 0. Okay, so since both of them less than 0, you conclude that 0.00 here is maximum point. Alright. Okay, and then once you done with the first stationary point 0, 0, proceed to the second stationary point, which is 4 over 3, 4 over 3. So your x is 4 over 3, your y is also 4 over 3. So substitute this into the Hessian that you found at first. Okay, so replace 4 over 3 for your x, and then you will get your Hessian equal to minus 8. So minus 8, is it greater than 0 or less than 0? Yes, it is less than 0. Once it is less than 0, the condition said whenever your Hessian is less than 0, then it is saddle point. So it is very obvious that your second stationary point, which is 4 over 3, 4 over 3, is saddle point because the Hessian is less than 0. Okay, let's say if you have another point, and that point after you substitute into Hessian, you got H equal to 0, then the conclusion that you made here in this column is no conclusion. Okay, alright. Okay, so that's it on how to find or to classify the stationary point. I hope this example is enough for you, okay, to see what happened, how to classify the stationary points that we've got from the setting of del f del x equal to 0 and del f del y equal to 0 for a function. Okay, right, if you are still weak, okay, you still dizzy and does not understand well on the process of finding and identifying or classifying your stationary point, you can refer to this flow chart. Okay, so I found this from the internet, and I think this is a good flow chart to for you, okay, to refer to the flow of finding the stationary point until you can determine or classify your your stationary point. Alright, it's just that something that you need to take note here is, alright, your Hessian here is defined by this, okay, by delta. Alright, so the symbol for Hessian is this. Okay, this is also Hessian, 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 and Hessian. Okay, so this is for the these two is whenever your Hessian greater than 0, and this is Hessian equal to 0, This is Hessian less than 0. Okay, and we use function, we define our function as f, but in this flow chart our f is equal to z. Okay, so the function is defined as z. So that's it, the difference between what we use in this course and this flowchart. Alright, so because this flowchart I found it from the internet, so the notation might be different a little bit, but don't worry, notation is just what we believe that we let something to be, but they bring similar meaning. Alright, okay, so that's it for this course, and this lecture or this video marks the end of our lecture, and you can start preparing and completing your tutorial. Okay, get ready for your test 2, which will cover everything that we have learned in chapter 5. Alright, and then once you're done with your test 2, you have completed your EQT 101 for this semester. Alright, I hope to see you again this Tuesday. Thank you very much for listening. Assalamualaikum.